1 second.
Fine.
Can you see the screen?
It's perfect, like, okay.
Okay. Okay, so I'll talk about embedded chimera states in recurrent neural networks. This work I'm doing at the University of Calgary with Bilten Nicola and Jörg Davidsen. I'll first remind you what a chimera state is, although we have already seen them and a lot of people are working with them. So chimera states, as you may know, are coexistent domains of coherent and incoherent behavior. Here I have a nice example of mechanical oscillators or metronomes, and we can observe that we have a population that is synchronized and a second one that is not synchronized. They are homogeneous oscillators and they are hierarchically coupled, meaning that the oscillators that are within one population are strongly coupled and the other ones are weakly coupled, so to the other population. Chimeras has been studied in a lot of systems. They start studying theoretically in a ring of non-locally coupled oscillators. We have here a non-local coupled ring, and here we have the phase of those oscillators, and we can see that some of them are synchronized and some of them are not synchronized. Recently, also chimeras have been studied in multi-layer networks, as the figure that we have here. And you can see that the red dots indicate also this is the phase of the oscillators and the number of oscillators. The red part is the synchronized one, whereas the blue is the synchronized one. Also, chimera states have been studied experimentally. Here we see an example of optical oscillators where the yellow part is the asynchronized one. And also in chemical reactions, here we have the snapshot. So it's that denotes an oscillator, and we have again the synchronized and the synchronized part. And on the bottom, we have the time series. Chimera states have been linked to the unihemispheric sleep of dolphins. That is that dolphins can travel a lot long distances, and that's because half of their brain is awake and half is sleeping. And the awake part is not synchronized, whereas the sleepy part is synchronized. And this can be seen as a chimera. And also, a nice example of chimeras is that they have been used to detect, or they aim to be a useful technique to detect epileptic seizures. As you can see here, we have the phase of different channels of this channel records the electrical activity of several neurons. And we can see that before a seizure, some of these channels are not synchronized and the other are synchronized. So this could be seen as a chimera state. And after the seizure, like the different channels, they end up being synchronized. And actually, I want to focus on this second example because, as I already mentioned, each channel records the activity of several neurons. And then we observe that there is a chimera. And one question that arises is how the microscale, so how the individual neurons are organized in the micro scale and in order to have a chimera on the macro scale. So this leads me to the aim of this work. And we want to understand how a chimera state emerges in a neural network. And in particular, how does the microscale of this neural network organize to have a chimera on the macro scale? There have been works on that. The thing is that they have been done from top to bottom. That means that there has been some, well, not some, but quite a lot, analysis on some mathematical models, where then there has been observed a chimera, and then this has been related to brain models. The thing is that the brain is quite complex, so some of these models lack important features that the brain needs. So here what we propose is a novel approach, and what we want to do is to take a real biological network, to train this network using a machine learning technique, and then to understand the dynamics underlying it while this network performs a chimera state. And we are going, so now I can move to the methods. So as I said, we will train a recurrent neural network to perform a chimera state. and we will use the technique that is called force training. Let me first explain you what a recurrent neural network is. We have the dynamics of each node on the first equation. So Z can be seen as the currents of neurons. Neurons receive a lot of currents, and Z can be seen as those. The firing rate is defined as a sigma function of those currents. And then an important definition is the output of that network. The output of the network is defined as a linear combination of the firing rates, and the weights are given by this phi here. And as you can see here, we have two different sets of weights, the omega sub 0, which are strong and fixed and sparse, so we don't have a lot, and is the initial network connectivity. And then we have a second set of weights, which are given by theta and phi, and those weights, they will change so that the network can perform the given complex signal, in this case, a chimera state. And I will be using a recurrent neural network of 1500 neurons. The number of neurons depend on the complexity of the signal. And the method that I will be using is named force training. And as I already mentioned, what it does is that it changes phi so that it enforces that our output, so the linear combination of firing rates, is equal to the supervisor or complex signal. And it uses an algorithm. It's the recursive least square technique. I'm not going to go over it, but you can have the reference here and read about it if you're interested. I think I explained more or less everything. So I want to show first an example of a simple signal. Here, our recurrent neural network will learn a simple signal, which is a sinusoidal one. We have the nodes. It's a homogeneous network. The color of the node just reflects different nodes, but they are equal. As you can see, I have already plotted the omega sub 0, which is the initial sparse matrix, but the strong weights. Here we would have the phi, which is changing, and then the firing rates. Let me play this. Yes. So here we have the firing rates. Now the network is learning, so the weights are changing and phi is changing until it settles down, and the network has already learned the complex dynamics. Well, in this case, it's not that complex. And yes, here we have the thing. So now I can move to the supervisor that I will be using. So our chimera state, let me show you first also the equations. It's a simple one. It's a two-couple population. It's similar to the metronome example that I already showed. And we have two couple populations. The nodes within each population are strongly coupled, and they are weakly coupled towards the other nodes. Here we have what we measure are the phases of those oscillators. It's a homogeneous population, both they are equal. And here we have the coupling within the population and with the other population. It's important, I guess, to remark that we need this kind of coupling to observe chimera states with there are not so many nodes, so that the chimera stays. And yes, also the initial conditions are important. Here I have the chimera state, actually. Here we have the time series of the phase of one of the populations. And as you can see, this one is synchronized. The three nodes, they have the same dynamics. And the other population, they are not synchronized. And here I have a nice video where you can see the synchronized population and the not synchronized one. Yes. And this is just a reminder of what we're going to do. So here I have the recurrent neural network, and I will change those weights here so that the output of the network is equal to the supervisor. And here I'll have 6 different supervisors, because we will have, for each population, we'll have 3 nodes, and we have 3 nodes here, 3 nodes here, so 6 supervisors. Now I can move to the results. And we see that the recurrent neural network learns the chimera state. Here I have the supervisor plot and the network output. And now let me play again. And here I just plotted as a reminder the firing rates. So this is what is the recurrent neural network doing. And as you can see, they are performing the same dynamics as a supervisor. A second nice result is that this is robust. So this result is robust to the change of weight matrix. A thing that I did not say is that the static weights omega sub 0, they are drawn from a random distribution. So we trained the network with several, here I just plotted 4, but we did it for 10. And with the different omega sub zeros, we obtained the same, so that the chimera was learned, meaning that it does not depend on the initial conditions of regarding omega. And this, it's also a nice result. So our network learns, even if we apply the Dale's law. Let me explain you briefly what Dale's law is. So Dale's law states that a neuron is excitatory, and it means that all the connections this neuron will have, they will lead to the increment of firing rates to the other neuron. Whereas if it's inhibitory and this neuron has connections, it will lead to the decrease of the firing rates to the neurons that it is connected. So this Dave's law on the results that I just showed you, I didn't, so it was not implemented, but we did. So here what I'm showing to you are the static weight matrices. This is the omega sub 0, this is the learned weight matrix, and this is the total. And as you can see here on the first ones, there is no law applied. That are the results that I just showed to you. And it means that the neuron here had different, so was excitatory towards one, meaning that it had positive weights toward ones or negative towards the other ones. Whereas on the second row, we can see that the Dale's law is applied, and we have excitatory, we can see the blue and the red, and this remains like that. I'm not going to show you that the supervisor is learned, but you can believe me. And also the result is robust when I increase the number of nodes at each population. So here, instead of 3 nodes per population, I had 25 nodes. And again, here we have a nice video. Here it's the supervisor. Now the synchronized population is on the right-hand side. And here I have the other. This is the network output. Here I did not plot the firing rates, but you can see that is the network output. And again, they perform the same, so that the recurrent neural network learns the dynamics of this other type of chimera. And almost at the end, and here what I want to say is that the firing rates contain information regarding the chimera state. And what I want to say with that is, so if we take the time series of the chimera state, so the synchronized population and the not synchronized population, and we perform a Fourier transform, we observe that we get 3 different frequencies. And these 3 different frequencies are actually also obtained when from the recurrent neural network, we take the firing rates and we compute the fast Fourier transform of the mean of those firing rates, and we obtain the frequency that was also on the chimera state. So this leads me to the conclusions and the next step. And as a take-home message, I would say that chimeras, can be embedded in a recurrent neural network. And next steps, we need still to understand how the connectivity of the neurons leads to the chimera state. So the initial question is not yet answered, but we are on the way to do that. And also we would like to determine the robustness of the findings using another chimera state. So far I work with 2 populations of coupled oscillators, and we would like to maybe just go with 1 population and see some synchronized and not synchronized. And so let me thank you for your attention, and that's it.
Thank you very much, Maria, for your talk. Very interesting. So we have time for questions.
Jean-Louis, can I ask a
Yeah,
question?
yes.
Thank you for the talk. It was very interesting. I have a question. You mentioned the dolphin, the
Yes.
fact that the dolphin sleeps on one side. So he has desynchronized activity on one side and synchronized on the other side. So this means that in another phase of sleep, it will be the opposite.
Sorry?
Is there a model? Well, it will sleep one side and then it will sleep
Exactly.
the other side, right? So this means that if you want to model this, you should have a model that is able to switch also. Is that possible? In the model you show, I think
Well, we could use a
you would need to
chimera.
switch the
Yes.
connectivity or something.
Yeah.
Right?
We could